Okay, final section of the course. You've almost made it. So the last thing we're going to deal with are improper integrals. And the best part about this is you already know how to do all the bits. If you've made it this far, you've been introduced to everything here. We're just going to put it together in a strange way. So an improper integral, there's one type we can deal with and one type we're not going to deal with. So the type we're going to deal with is the first one here. It's where at least one of your limits of integration is infinite. So we could have both be infinite, so negative infinity to infinity. We can have the other side, a to negative infinity. At least one of them has to be infinite for this to work. The other one is if we have a discontinuity on a point. So if we think about this graph here, it's always positive from the right side. We go here, left side, we go here. And it never reaches zero, but it gets really close. So we can deal with that as well. We won't here, but we're going to focus on the infinite, but that's the other sort. All right. How we deal with the infinite, there's three types. We go to positive infinity. We start from negative infinity. We're infinite everywhere. So if honestly, all three of these work the same way, it's just a matter of what your limits of integration are. So if we go from a to some positive infinity, what we do is throw the limit here as b goes to infinity. And then when we do the math, we just ignore that until the very last step. So mostly it's the same. If we start from negative infinity, we're going to do the same thing, except a goes to negative infinity instead of positive. Simple as that. If we have both, we break this into two cases, negative infinity to c to positive infinity, and then you use the cases above to make that work. So I don't want to say straightforward because it's kind of weird, but not the worst. If you're curious, the normal distribution uses this. So if you think about this, I'm sure everyone's heard of normal distribution. We have the bell curve, area under the curve. Your function here will never reach zero, but we can find the area under this curve using this bottom technique. So we fill this in. We know the area under the curve is going to be 1 based on our integration techniques over here. So we're skipping the probability sections due to time, which is a real shame because that's where, we use this stuff. And personally, I find it interesting that I know I'm a math person, so this to be expected. But that's where this comes into play, and that's really useful. Okay. If the limit of our integration exists, our series, or not series, wrong section, our integral converges. If not, it diverges. So if you recall, converges means it goes towards a certain value. Diverges means it's going to go towards infinity in the end. So let's jump to it. So we're going to say this equals the limit. I use b for my top value. 1 to b, 1 over x dx. Okay, pretend that limit isn't there and integrate. So limit as b goes to infinity. The antiderivative of 1 over x is just natural log of x. And my limits of integration go from 1 to b. Plug this in, right? Yeah. Ooh, drop my pen. All right, natural log of b, natural log of 1 is 0, right? Let me double check. Okay, so as b goes to infinity, what happens to natural log of b? I should probably remember this, but today I do not. I'm going to plug in some really big values. All right. Sorry, let me cheat a sec. My calculator does limits. Natural log of x. X. I think this diverges. Yeah, it does. So the limit as b approaches infinity is infinity. So it doesn't converge to a limit. So we just say diverges. When in doubt, throw in some really big values for b and see what happens, which is what I did. I don't deal with that function a lot. All right, hopefully this dude here will converge for us. Okay, same thing. All righty, 1b, x to the negative third dx. As b goes to infinity. All right, antiderivative of this is negative 1/2 x to the negative 2. Let me go from 1 to b. Alrighty, so plug in b, I get negative 1/2 times 1 over b squared minus negative 1/2 times 1 over 1 squared. That is a mess. Okay, multiply here, I get negative 1 over 2b squared. That's fine. All right, I have a double negative. This is just going to turn into plus 1/2. Yeah. All right. Now, as b goes to infinity, what happens? Well, we're getting really, really, really big numbers on the bottom here. So I get negative 1 over infinity. Well, that's going to go to 0. So I'm just left with 1/2, and we converge. So that's our limit. All right, this is our last problem. Same idea. All right, limit. This time I'm going to use a goes to negative infinity, a 0, 1 minus 2x to the negative 3/2, not 3/3, dx. All right, I am going to use a u substitution. Okay, so do a u sub, move things around a little bit. All right, bring this outside, negative 1/2, a 0. And this gives me u to the negative 3/2 du. All right. I add 1 which is -1/2 times, oh, hang on. I have that -1/2 hanging out here already. Times the reciprocal of this, which is -2, 1. So this comes from here. And we go from A to 0. Well, that's a disaster. Okay, so this just gives me my u, which was 1 minus 2x to the -1/2 from A to 0. Plug things in. All right, 1 over 1 minus 2 times 0 to the 1/2 minus 1 over 1 minus a minus 2a. This just goes to 1. Okay, we're going to plug in negative values that get really, really big. So my denominator gets really, really big. So this should just give us, that goes to 0, we just get 1. And that's our final answer. Okay, that's really it. Most of these are fairly straightforward despite being kind of weird. Give them a shot, and that's it. We don't have anything else. So it's been fun, and I will see you when I see you.